We are deep into the world of string theory now. We've met the tachyon, which threatened to bring the entire enterprise to an end. But we also found out, thanks to the initiative and industry of three young physicists, Nevers, Schwartz, and Ramon, that there is a way to get out of this trap. There's a way to find Pandora's box. And once this way is used, then the tachyon is banished and string theory becomes more like our world. An important ingredient in this is, in fact, to incorporate something of our world into this mathematics. The first generation of string theory had no electrons, had no quarks, had, roughly speaking, nothing that corresponds to the matter in our universe. If we look at our familiar table of denizens, the leptons, namely the electron and its friends, we find out that there are lots of objects that spin at a rate of 1/2. So the electron is the E on our table here. The mu is another particle 200 times as heavy as the electron. The tau particle is another particle 1700 times as heavy. In addition to the electron, we also have the quarks: up, down, charm, strange, top, and beautiful. And all of these objects act as though they are spinners. And we now know what spinners are. That was one of our great discoveries. These are things that sound almost like they're from science fiction. If you think of them as an arrow, you walk around a spinner once and look at it before and afterwards. And when you look afterwards, the arrow is pointed away from you. You walk around it twice, looking again before and after beginning your journey, you find out it's pointed towards you. And for every even journey around, it's pointed towards you. For every odd journey around, it's pointed away from you. This is a property of all quarks and all leptons. But they have an even stranger property, and that's the one we're going to visit with in the lecture today. The universe of mathematics is a playground for the human imagination. We make up numbers, but often with hints from nature. But sometimes she is not so immediately obliging. Humans often seem to have an almost instinctual neural software that manifests itself as an affinity for numbers. For those of us who carefully study fundamental questions about physical reality, it often seems as though nature is as teeming with mathematics as our planet is teeming with life. We come across different number systems at various early stages of our life. For example, the counting numbers, then the number 0, fractions, the so-called transcendental numbers such as pi. These are things that most of us encounter in the course of going from, say, 1st grade to 12th grade or to college and beyond. For the counting numbers, we can surmise that one of the first lessons learned by humanity was how to count items that constituted food. The question of how much is not an abstraction when it's part of the issue of survival. So at some point, one can imagine a herdsman going to sleep one night, counting the numbers of animals in his or her flock, and then wanting to be sure the next morning that the same number of animals was there because our survival depended on that. So at that point, humanity, the human family, gains what we might call numeracy, the analog of literacy, the ability to abstract numbers in the world around us. Now, counting is fairly obvious. In fact, many ancient systems developed numbers, across the course of history. A fair number of them, interestingly enough, did not include the number 0. Positional notation, well, what do we mean by that? Well, when we modern people write a number like 123, we write the 100, the 1 to the left, followed by a 2, followed by a 3 as we read from left to right, meaning 100 plus 20 plus 3. And this idea of positional notation seems to have appeared first in Babylonia and India. The number 0 seems to have occurred sometime between the period of 200 and 650 AD. It took almost 500 years for the present Arabic Hindu number system to be accepted in Europe. Also, fractions in Europe were not generally used as they are today until the 1700s. And on the other hand, there's evidence that as far back as 1800 BC, the Egyptians were writing fractions in a base 10 type system. And similarly, China had such a rich history of using fractions that dates back to about 100 BC. Now, of course, when you come to a course on string theory, you don't expect to hear about mathematics, and yet the recitation I just gave you was all about mathematics. The transcendentals, by the way, of course, is the famous pi discovered by Archimedes. Sometimes, however, nature is not so instructive about numbers, and we have to dig a bit to get to them. String theory makes use of all kinds of mathematics. So today's lecture, this lecture, will be about another piece of important mathematics for string theory, which turns out to be critically important in the removal of the tachyon. Well, I don't have a dollar bill in front of me, but if I did, if you look at what's called the opposite side of the dollar bill, there occurs a frustum. Now, what's a frustum? Well, I have a little movie here which makes it simplest to see, so let's visit the movie. Let's begin with a pyramid that has a square base. So there it is. Now, let's imagine we start chopping off the top of the pyramid in a line that's parallel to the ground. So there we are, cutting the pyramid down. And now, this object that I achieve after I've cut off the top of the pyramid is the so-called frustum. Now, as I said a moment ago, if you look at a dollar bill on the opposite side, you'll find this shape there with an eye that appears right above this shape. It's called the Eye of Providence, a Masonic symbol. But what we want to address ourselves with the frustum is a problem that's actually very famous in human history. So here's our frustum. Let's continue to rotate it so we'll look at it from different angles. And now, let's imagine that I take some sort of measuring rod and simply pace along the bottom of one side of the frustum. I can get a number for that length. We're going to call that number B. Now, again, since it's a real object, imagine climbing to the top of it and measuring the similar number that goes along the sides on the top. We'll call that number T. So this is the length of the top and the length of the base. And now finally, there's one other number I'd like you to imagine. Let's imagine that we can dig a hole from the top of the frustum directly down to its bottom and take some sort of measuring rod along with us in this direction, and we'll call that number, whatever it is, we'll call it H. Now, what's the problem? Well, this object is a real object. It has a volume. And if it were an ordinary box, it's very simple to figure out that volume. It would be the area of the base times the height of the box. But this thing is clearly not a box. It's something more complicated. So, how do you find the volume for this? Well, with the invention of calculus via Sir Isaac Newton, as well as Leibniz, it's a simple problem in integral calculus to figure out this volume. But, remarkably enough, the formula which answers the question for the volume seems apparently to have been known to the Egyptians, and we're not quite sure how they worked that out. Nevertheless, the answer turns out to be that in order to find the volume of the frustum, one takes its height. Remember, the height is digging the hole through top and bottom. You take that number, multiply times the square of the base. So we marched along the bottom of the base to find that number. Then you add to that the product of the base distance and the top distance. So you take the product of the length along the bottom, multiply that number by the length along the top, and then finally add that to the square of the length along the top. So we take the length here and basically calculate the area. You take those three numbers, you divide by 3, you multiply by the height, and there's the volume. Well, as you can see, that's a pretty daunting process. And in fact, if you stop and think about this, the way I've talked about measuring this volume has one extremely difficult part. Namely, you can imagine that it's fairly simple to march along the base of what would be the pyramid. As well, it is fairly simple taking a measuring rod to measure the length of the top. But do you really want to drill down through the bottom of from top to bottom of the frustum. That's a lot of work. So, this presents us with an opportunity. Instead of destroying this object that we're building, we imagine that we're ancient Egyptian engineers constructing this. Instead of destroying our work, there's something else that you might imagine. Instead of actually digging from top to bottom to measure the height, there's another height that's easily measurable. Namely, let's just take some sort of measuring rod and lay it along this edge of the frustum. That's easily measurable. We don't have to destroy our engineering marvel in order to get that number, and it's an easy thing to find. So the question is, suppose instead of the height from top and bottom, we instead measure this length along an edge. How is the volume related to that? Well, this is a problem, again, that one has to sit down and draw some figures. It's the kind of thing we do in geometry. This is what geometry is good at. When you do that, what you find is something very interesting, namely that the height through the middle, that's going from top and bottom, is actually related to the distance along this edge. We're going to call that distance S for slant edge. And the relationship is that in order to get the height, you take the square of the side along the slant edge, you subtract from that 1/2 of the differences of the base length, and then subtract from that the top length, square that, and take a square root. Wow, that's a mouthful. But nonetheless, it's actually easier to know this piece of mathematics than it is to dig down through the frustum. And the ancient Egyptians actually knew this. Again, we're not completely sure how they worked it out, but we have lots of evidence that they did. Now, this sets us up for a struggle that takes about 1,500 years of human history. You see that formula that we have sitting here, that h is equal to the square root of the slant edge squared minus 1/2 of the difference of the lengths of the bottom and the top, that formula leads to something interesting. Suppose it were the case that the S term, which I'm pointing at here, is actually smaller than the difference term. Then, in fact, since this thing is smaller than that, you try to take the square root of a minus number, of a negative number. Now, the thing that's interesting about that is that it took 1,500 years before we as a species figured out how to take the square root of a negative number. This problem arises as soon as you think about the frustum, and as someone of mathematical bent, decide that you're going to play with this formula. You find out that, gee, you've got to take square roots of numbers that have negative signs. Now, the problem with that, of course, is that if a number has a negative sign, it's not obvious what the square root should be. Because, for example, if we take -1 times -1, that's actually +1. If we take +1 times +1, that's also equal to +1. But there's nothing that you can immediately put your hands on that when you square it, you get -1. In fact, it calls for us to do something that some of us are a bit uncomfortable doing, and that is to make up numbers. It is a human facility to make up numbers just like we make up music. Now, this may sound odd or strange to you that, boy, we're allowed to make up numbers, but yes, we make up numbers. And so, the way to solve this problem of finding the square root of -1 is to make up a number. There's actually a book about this whole process. It's called An Imaginary Tale, The Square Root of -1, which I recommend highly for someone who wants to understand how we struggle as a species sometimes to make up numbers. Solving this problem of square root of -1 leads to what are called imaginary numbers. Now, as a teacher of mathematics and physics, I always have to smile a little bit when I introduce the idea of imaginary numbers to my students. And you might wonder, what's the joke? Well, you see, most of the numbers that we use, we sort of think about as being around us. I can have 1 glass of water, I can have 2 glasses of water. So the notion of 2 is connected to things around me. And so in some sense, the number 2 seems very real. Or perhaps I have 3 glasses of water. That makes the number 3 very real. If I want to think about fractions, well, give me a piece of cake and cut it in half. Gee, I have half a piece of cake. So the number 1, the fraction 1/2, is again connected with something in the world around me. Things like pi, well, that's a little bit more difficult. I have to take a circle, take a tape measure, and lay it around the edge of the circle. That measures its circumference. And then I take the tape measure and measure along the diameter, the longest chord of the circle. That actually gives me twice the diameter making that measurement. If I take the ratio of those 2 numbers, I can use that to define pi. So the number pi is somehow connected with the shape of circles. There are lots of other such numbers called transcendental numbers that mathematicians, physicists, and humans have been discovering over the years. There's something else called E, that is the natural log, very useful for taking logarithms. So numbers normally seem attached to the world, and that's the way that we as a species, I'm sure, came to our numeracy. But sometimes it's required that you think of objects that don't seem to be in the world around us. The eye is one such thing. So now let me talk about another property which you won't be surprised about. Suppose I wanted to buy a carpet to cover this stage. And let's imagine that the stage is not quite square. I would take a tape measure and measure along the front edge of the stage, measure along the side. That would give me 2 numbers. I would multiply those 2 numbers and go to a carpet store and say I want, for example, let's say we got 4 feet across the front and 3 feet across the side. I'd go to a carpet store and say, I need 12 square feet of carpet to cover my stage. Now, how did I get 12 square feet? Well, I took 4 times 3. That gave me 12. But what's wrong with taking 3 times 4? Why can't I take the 3 first and multiply by 4? Doesn't that give me 12? Well, the answer is yes. Of course it does. So one of the things that's really interesting about how to measure areas is it doesn't matter which number you put first. We can write this as an equation, and in fact I've done this on the transparency. I've written that 3 times 4 minus 4 times 3 is equal to 0, which is true because each of them is 12. Well, rather than talking about the numbers 3 and 4, we can pay homage to algebra as originally brought to us from Iraq, and instead of writing 3 times 4 minus 4 times 3 is equal to 0, we can use letters and write A times B minus B times A equals 0. Means the same thing. Well, in the 1800s, between 1844 and 1862, a mathematician by the name of Grassmann decided to throw the rules all the way. He said, I don't want the usual rules to be true, namely A times B minus B times A is 0. I want A times B plus B times A to be equal to 0. He exactly reversed the rules. Now, the thing that's really interesting about that is if A and B are the same number, then this says that a number times itself is 0. We know of no such numbers like that in the world around us, except for 0 itself, right? 0 times 0 is equal to 0, but there's nothing else that has that property. Well, mathematicians, of course, are not tied necessarily to the real world. If you give a mathematician a set of ideas, what they want to know is whether these ideas are logically consistent. And it turns out that they are. You can have numbers where that let me say it this way, there's a kind of number which we now call the Grassmann number, named after the first mathematician who thought of it. If this stage were made of Grassmann numbers, when I measured the 4 feet across the front times the 3 feet across the side, if I do the multiplication in one order, I get 12 square feet. But if I do the multiplication in the other order, I get minus 12 square feet. I don't know how to go to a carpet store and order minus 12 square feet. The salesman would look at me and wonder what my issues were. Well, the thing that's remarkable is that instead of talking about measurements along the edge of the carpet, there are things that obey Mr. Grassmann's rule. And perhaps you might be surprised to know, but some of these things are electrons. It turns out that if you take two electrons and try to measure properties simultaneously, they obey Mr. Grassmann's strange rule. Let's do this slowly by first talking about things that act like lengths. And those would be the photons. Photons act pretty much like ordinary lengths. So let's put a transparency up here to help us through this. If I take my carpet example, where I have 4 times 3, that's the same thing with a plus sign as 3 times 4. And that's what I can order in a store. On the other hand, according to Mr. Grassmann, I should be allowed to think about a number where the opposite sign occurs. The first one we call commuting multiplication. The second we call anti-commuting multiplication. And now let me tell you the amazing thing about our world. You see, if I take 2 photons and try to measure their properties in the order 1, 2, and then compare that with measuring the same property but taking the photons in order 2, 1, in our world, these both give the same result. And in terms of mathematics, it's appearing on my transparency now. We say that the property of the first photon times the second is equal to the property of the second times the first. Well, that's just like our measurements of area. On the other hand, if you take 2 electrons and measure a property that relates to the 1 electron, call it electron 1, and then a property that relates to the second electron, and then compare that to the measurement where you measure the property on the second electron first and followed by the property on the first electron, you get a minus sign. The minus sign you find is exactly Mr. Grassmann's minus sign. And the remarkable thing about that minus sign is that it is the source of chemistry. You see, the reason you can't put 2 electrons in the same place at the same time is because if they were, there would be no way to distinguish them. But according to Mr. Grassmann's rule, 1 electron times another is minus the order. But if they're the same, it says something is equal minus itself. The only way something can be minus itself is that it's 0. You can't put 2 electrons in the same place precisely because they obey this weird mathematical rule of Mr. Grassmann. Now, for us, and we want to use this in string theory, remember that for the string, we're allowed now with the so-called spinning string or superstring to have modes or vibrations that have the properties of electrons. So that means modes of vibrations or the notes of the string that have the properties of electron, when you interchange their order, give you a minus sign. So now we are in position to eliminate the tachyon. How does it work? Well, let's imagine that we had the tachyon where it somehow, for example, bounces off of 2 objects like the electron. When it bounces off them in one order, you'll get a plus sign. When it bounces off of them in the opposite order, you get a minus sign. And now, the way the rules of the quantum world work is that anything that can happen must happen. So now, let's go back to our full new string that has both fermions and bosons. Sometimes fermions bounce off the tachyon in one order, and then another time there's a probability that they'll bounce off in the opposite order. Since the 2 events should have the same probability, one gives a minus sign relative to the other. On the other hand, let's let our tachyon bounce off of bosonic modes of the string. When they do that, then the order in which the bouncing occurs doesn't matter at all. And now, something quite remarkable happens. When you ask, what's the impact of the tachyon, not on itself, but on the things that it's bouncing off of? It turns out that when you look at the possibility of bouncing off of fermions with their funny minus sign, or bouncing off bosons that don't have the minus sign, then you can make a miracle occur. If the number of fermion bounces is equal to the number of boson bounces, then the tachyon has no effect on the fermions or the bosons. This is quite remarkable. By having an equal number of modes that act like the electron and that should be equal to the number of modes that, roughly speaking, are like the photon. If you arrange for that to be true, it is as if the tachyon is not present in string theory. So it was discovered that when you have the property where there are equal numbers of bosons and fermions, it is as if the tachyon is not present at all. In other words, there's a special class of models where you set the number of boson vibrations equal to the number of fermion vibrations, and when that occurs, we've got our Pandora's box. The Pandora's box is to work in the models where the numbers of modes are the same. Now, it turns out that there are lots of different ways to do this. The simplest way of doing this is what's called the n=1 spinning string. So we take the n=1 spinning string and we allow for equal numbers. And when you do that and ask, how is it possible for this string with both sets of modes to vibrate, you find out all of the modes of vibration obey the Einstein hypotenuse. So all of them look like particles in our world. But something else very remarkable happens. You remember in the original version of the bosonic string, there were two problems that occurred because of the probabilities. We had to have 25 directions, and the tachyon had to be banished. Recall, when we talk about spatial directions, we have the idea that there's something like the Einstein hypotenuse that extends all the way from 1 to 25 in terms of spatial directions. But we're always including time. So we physicists use the numbers 25 and 26 interchangeably. When we say 25, we mean 25 spatial directions, 1 temporal direction. In this new generation of strings, it turns out we have banished the tachyons by having equal numbers of bosons and fermion vibrations of the string. But what is more remarkable, perhaps, is that if you ask, well, how do these modes of vibration satisfy the Einstein hypotenuse? The answer turns out to be you only need 9 spatial directions, not 25. In other words, you need the 3 directions that we're familiar with in our everyday experience of physics, or plus an additional set of 6 directions. Well, 6 is much, much less than 25 or 22. And therefore, the superstring, with its equal numbers of bosons and fermions, looks more like our universe. But that's great, because in our universe there are things like electrons. We want there to be things like the electron that have a half a rate of h bar as its spin, and thereby includes the Pauli exclusion principle. And so when this was discovered, that it was possible to include superstrings, it was an enormous boost for string theory. Now, it hadn't yet become physics, but it meant that we could get rid of the embarrassing problem of having probabilities that were greater than 1 or less than 0. In the superstring, it turns out all the probabilities are between 0 and 1. And that's consistent with our view of the quantum world. In the quantum world, probabilities can only be between 0 and 1. Well, the story is a little bit more complicated than that, because it turns out that there are more complicated ways to accomplish this banishing of the tachyon. One of these more complicated ways is to include even more fermionic particles, more things that obey Mr. Grassmann's number rule. The next most complicated set of objects is what are called n=2 strings. n=2 strings are really bizarre. Most of the time, we physicists don't talk to the public about n=2 strings. And there's a simple reason for why we don't do that. You see, if you ask for the Einstein hypotenuse for what we call an n=2 string, you find out that you need 2 time directions and 2 space directions. That's nothing like our universe. And so the n=2 string you probably have not heard of in the popular literature, but it exists for us physicists. We've been studying this strange object for almost since its inception in the literature. And now you say, well, gee, why stop there? Maybe you can do more. The answer turns out to be, yes, we can write even more cancellations, banishing the tachyon, but none of these others look at all like our world. And the other thing is, if you do more of this same kind of adding fermions, what you find is that the tachyon comes back in a different guise. Not the original tachyon, but new tachyons occur. And so the numbers of strings that we can actually write that keep the tachyon in Pandora's box is relatively small and include all of the ones that you've heard about, for example, in works like The Elegant Universe or in hyperspace.